fine. Okay, we are going to do some couple things here. Would someone please for me define universal gravitation? Universal gravitation. Just give me a definition, and someone else will give me an equation. Universal gravitation.
Calculated between any two objects if their masses and distances between them are known.
Yeah, this is sounding suspiciously like someone with a PhD wrote it, but I do like that definition. Drew it right out of the book. Let's recombobulate that into our own freshman thoughts and say it again.
Two objects.
Okay, not like a caveman necessarily, but we'll say that, any two objects. Where?
Have gravity.
Sure, I like that, but where at? I'm going to include the where. No.
In any particle or matter in the universe.
Yeah, any two objects.
That's why it says
Particle or matter, which matter is particles and particles is matter. So particle / matter in the universe, in the entire universe. That's why it's called, someone correctly points out, universal gravitation. Any two objects are attracted to what?
Center.
No, I'm looking for something else.
center.
Yeah, that's true. To each other by gravity. And then obviously the thing is, it's not just these two objects are attracted to each other, but those two objects are attracted to each other, and to that object, and to that object, and to that object, etc., times infinity. Everything with mass in the universe is attracted to every single other thing with mass in the universe. And we can calculate that, and it can be mathed. It can be mathed how? What's the equation? For anything. For universal gravitation. Say it. Someone has to have it. Okay, F sub g, the gravitational force, equals big G. Big G.
G, which is the constant, right?
Yeah, the universal gravitational constant.
And then mass.
I like to put this one into parentheses. I think it's cuter. Mass 1 times mass 2 divided by the distance between them squared. So if we know the mass of any two objects, and we know the distance between them, and we know math, and we know the universal gravitational constant, which actually was found in, I think, the 1700s, so not everyone always knew this. We can calculate the strength of gravitational attraction to them. So, F sub g equals, g is always, sorry, I should put is. F sub g, what is F sub g? Is, what did we just say? The force of gravity. Give me another word for the force of gravity. No, it's not always a net force. Remember, net forces are only those that are unbalanced. What's another word for the gravitational force that starts with a W? Weight. I'm going to put weight. What do we always measure weight in, or really any force? And I shouldn't say always, but what do we usually in the SI? We use newtons. In the imperial, we use pounds, but we're not going to deal with that right now. Capital G is the universal gravitation constant. And this number, you do not have to have this memorized at this point, but you should know it, or you should be aware of its existence, is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Is this a very large or a very small number? Let's try again. It's extremely small. It's 0.10667, and then it goes on for a while after that. It's extremely small. I'm trying to think of exactly milli, micro, nano. If this is 1, then this number is about the width of a very, very thin human hair. I don't have very thin hair, but if someone had it'd be like that. It's very, very small. So basically, whatever, we're going to multiply these together and divide it by this squared. We're going to multiply by this exceedingly small number. That's going to give us a force that is really quite small. You remember from last year of the 4 fundamental forces that gravity is the weakest force in the universe, the weakest of the 4 fundamental forces. Okay, M1 and M2 are what? Masses of the two objects measured in kilograms. And D is distance, the distance between their centers, which is measured in. Is Gary the only one here today? What's distance measured in, babies? usually meters. We'll say meters as the base unit, but kilometers would work. We just have to, since meters squared is in this unit, we'd have to reconfigure some things. So meters is probably the better one to use. And it's once again, the distance between their centers. Because if I have, you'll find that these are objects, right? You're aware that these are objects. They both have mass, so they are technically gravitationally attracted to each other. We don't observe that gravitational attraction. Why? If I let them go, first of all, we don't observe it right now because I'm holding on to them. If I let them go, will they be attracted to each other?
No.
Technically, but what will we observe that and why not?
Because of the gravity.
Because the Earth's gravity, because the Earth is right here, and she's a lot bigger than these things, and so they're much more gravitationally attracted to that. Just a little bit. The Earth is right here, and she's much bigger, and so we don't observe this, we observe that. Now, is the Earth also gravitationally attracted to these? So check this out. If we plugged in the numbers here, mass 1, what do these have a mass of, would you guess, in kilograms?
0.1.
0.3. I would say 0.3 is a pretty good guess, maybe 0.1, somewhere between 0.1 and 0.3. So we plug in 0.1, and we plug in the Earth's mass, which is 6 point something times 10 to the 25th, I think, divided by the distance between them. How far is this from Earth?
Like,
Be careful, because we already said, someone earlier said, I didn't write it down, but someone earlier said it's the centers. It's the centers. So it's probably about, I think it's about 2,400 meters. So we would multiply 2,400 times 2,400, multiply my 0.1 times my 6 times 10 to the 25th, divide it by that, multiply it by this very small number, and we would get a weight of about 10 newtons, probably, for this. Now, algebraically, what happens if instead of saying mass 1 is my marker and mass 2 is the Earth, what if I say mass 1 is the Earth and mass 2 is my marker? Nothing changes. The transitive property tells us that that is going to be the exact same, no difference, which also tells us Newton's third law, which is that the gravitational attraction between the Earth and this is the exact same as the gravitational attraction between this and the Earth, which is, in the Earth's field of gravity, this has a weight of about 10 newtons. That might be an exaggeration. Somewhere between 1 and 10 newtons, I don't actually know. But also in this is gravitational field, the Earth has a weight of about between 1 and 10 newtons. They're attracted to each other equally. That's Newton's third law. And you remember my joke. You can at least say, and let me tell you, the 8th graders this year, you know them, they thought this was hilarious. I told them that this, you can use this as a pickup line. You can say, girl, let me get those digits because you're already attracted to me. Because it is true, right? Everything with mass. And the more massive you are, I don't mean to look right at Lucas, the more massive you are, actually the more attracted to other people you are gravitationally and vice versa. So, especially if you're, I could do this, but if you're a big fella, you can go to the ladies and say, girl, I already know you're attracted to me. In fact, you're more attracted to me, technically, than this other little scrawny feller. And therefore, let me get those digits. For some reason, that made me blush. Do you have questions about universal gravity? You may...
Leave the second period.
Yeah.
Bye, Mr. Khan.
Well, we'll talk about centripetal motion and projectile motion on physical science time. We're going to real quickly today run over, hello, my sweater is getting run over. We're going to quickly today run over not just my sweater, ooh, that was scary, but also, where'd my marker go? Where'd my black marker go? Okay, we're going to quickly today run over, we talked about universal gravitation in the last part, which will be smushed in with this video, and we're going to talk today about projectile motion, momentum, and circular motion. Let's start with momentum. Projectile motion, momentum, circular motion. A lot of things in this chapter. Let's start with momentum first. We just talked about how momentum is the measure of an object's mass and its velocity. It's how hard it is to stop a moving object. On what quantities does momentum depend? Well, this is momentum. M is, what's M? Mass, measured in usually in the SI, kilograms. V is velocity. Now, is V also speed? Yes, the answer is yes. V is also speed. But remember, velocity is speed with direction. So what does that tell you about momentum? What? Momentum also relies on direction. Momentum is a directional quantity. Momentum is a vector quantity. And we measure velocity in meters per second. So if mass is kilograms, velocity is meters per second, what is momentum measured in? Kilogram times meters per second. We usually just say kilogram meters per second, or we sometimes say kilograms dot meters per second. But that little dot just means that those units are multiplied together. Now, we briefly talked about how if an object is stopped, does it have inertia?
No.
Try again. If an object is stopped, does it have inertia? Yeah. Remember, inertia is how hard it is to change an object's motion. That's Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force or an outside force. And that's whether it's stopped or in motion, just like the law says, that's inertia. But momentum specifically has to be moving. How much momentum does anything have if its velocity is 0? 0, yeah. Remember also that velocity is relative. Speed is relative. Basically, the question is compared to what? Like, do you have momentum right now?
Yeah. No. The Earth.
The Earth, yeah, okay. So Tommy, I think most of you are just wrong, but Tommy is right. You, as an object right now, compared to Earth's surface, do not have momentum because your velocity is 0, right? Yeah. Compared to Earth's surface, goes without saying. But as an entire object, the entire system of Earth has an enormous momentum because it has a huge mass, which includes you, and it has a huge velocity relative to the sun, for instance, that includes you. And so, even though you have no momentum right now as a singular object, if the Earth suddenly just crashed into Mars, the momentum would be very noticeable because we as a whole are moving. Questions about momentum and how to calculate it? Fine. Okay, let's talk about projectile and circular motion. Projectile and circular motion. What is a projectile? Vomit. It's vomit, and we're talking only and specifically about vomit, right? No, come on. What is a projectile? Did Lucas projectile vomit in the hallway in 3rd grade? Oh, bless him. Bless him. One time, this is not what this class is about, but one time when Asher was a tiny, tiny baby, not even 1 year old, he sat up in bed, and he went, "Bah!" And it went all the way to the end of the bed, and he also, this is so embarrassing, because he's going to watch this someday when he's older, he's going to be saying, "Why did you talk about me like that, Dad?" But it is the truth. He also, at the same exact time, filled his diaper completely up with diarrhea at the exact same time, and then he went, "Whoa!" And I was like, yeah, that's exactly right. That is exactly right, Asher. I'm really embarrassed for having said that. I'm going to cut this out. But speaking of projectile vomiting, and speaking of, here, catch this. Here, catch this. Here, catch this. These are all projectiles. Do you see that? And what is similar about these things and projectile vomiting? Now, notice the shape of the path and also the drawing we had of projectile vomiting. It's an arc, which some people, one time I had a redneck friend who called it the rainbow. He was shooting a blow dart, and he said, well, that one had too much rainbow on it. And he meant that it had too much of a projectile arc. And what shape is this?
That's a rainbow.
It's a rainbow. What else is it?
Underwood. It's a semicircle.
Math, please. What shape is this?
Croissant.
Come on. Come on. Someone was in algebra last year. What is it?
We're in algebra this year.
Someone was in algebra last year.
But we can't remember.
Quarter mid.
P.
Paradiddle.
Predicate. What?
Paradiddle.
Paradiddle. Parentheses. Paragraph. Paralyzed.
Peyton, come on. What is it?
Parabola.
Thank you, Cody.
Parabola. Oh.
I'm really tempted to give Cody a rare mark, but I think what I should actually do is tell Mr. Snilly. I'm going to show Mr. Snilly this video, and he's going to first say, why did you badmouth your son so much, and why did you throw all those things, and how did those kids not know what a parabola is? But that is...
Oh, I do remember that now.
That's a parabola, and that's actually one of the physical definition of the shape of a parabola is the path something takes as it travels through the air. Excuse me. The reason it has this shape is because, and you need to write this down, has a constant velocity in the x and a constant acceleration in the y. Now, what do x and y mean? What axis is this that I have drawn here on the bottom, across? This is the x-axis. And what is this axis that I have drawn up and down? This is the y-axis. In the x direction, all projectile motion is composed of two components, an x, horizontal, and a y, vertical. As time goes by, right, every mark that I make is going to represent 1 second, for instance. This would be a really, really big parabola if that were true. But as time goes by, it moves the same distance every second in the x, every single second. And that's called, if it moves the same distance every second, what is that called? Constant velocity. Now, in the y, what force is affecting it in the y direction and only in the y direction? Yeah, because of gravity. Because of gravity, as it goes up, which way does gravity always work? BT does. It always works down, and it always causes acceleration. So as the object is going up, if it's going up and accelerating down, it must be doing what? No, it's not. It's what? If it's moving upward, but accelerating downward, it must be doing what with its motion? Come on, buddy. If I throw it like that, you can even... I ran out of good things to throw, so I had to throw my actual writing marker. What is it doing as it goes up? Is it going at a constant speed as it goes up? No, it is accelerating in what direction? No, it's accelerating down, but moving up. So it must be... Thank you, Lucas. Finally. I can't believe no one else got it. It is slowing down as it goes up. So it starts out with a pretty large change in motion, and then it's a little bit smaller, and then it gets quite a lot smaller every single time. Yeah, it's slowing down. So as it goes up, it's slowing down, and as it goes down, it's speeding up. It's speeding up because it's now moving down and accelerating down. Do you see how these lines get closer together as they go up in the y, but they stay the same distance apart in the x? Basically, in the y component, it's the same as if it were just thrown straight up and brought straight back down. In the x, it's the same as if it's just rolling off a table or rolling on a frictionless surface. At this point, what is its y component of motion? At the very top of its path, in just the y, it has done what? If I throw it just straight up, at the very top, what is its velocity? Yeah, what's its velocity? It's 0. It has 0 velocity. At the top, v sub y equals 0. Now, does it still have an x component of motion? Yeah, of course it does. The y gets smaller as it goes up, and the x stays the same all the time. So we call it projectile vomiting because just like if this is you and this is your mouth, the projectile is that it's taking a rainbow path. And that usually happens, this is like, I don't know, medicine, I guess, but this usually happens in babies because like when a little tiny baby gets sick, their stomach forcibly expels everything from both ends so that nothing is left in the system, so that if there was a bad little bug, that's gone. When you get sick and just throw up, your body's like, well, I gotta keep some of this stuff because I'm a big guy. I'm not gonna eject everything. That's why it's kind of a struggle for you to throw up. Have you ever thrown up?
Yes.
And sometimes you're like crying. Also, I bet you look like a wreck when you're done barfing. That's not what we came here to talk about today, but this is the parabola, and that also is true even in something like a bow and arrow follows a parabolic arch, or even it's about hunting season. This is supposed to be, it looks really like a musket, but this is supposed to be a firearm. A bullet even follows a projectile path, a parabolic path. It seems to us, from our video games, from Call of Duty, it seems like it just travels in a straight line, but it does also fall. There's a little bit of, as my redneck friend would say, rainbow to it. Now, circular motion is a whole different ballgame. Circular motion is any part of a circle. So it can be a whole circle, or it can just be a arc, just a part of a circle. But this is when there's some force acting inward. There must be a force acting, ignore that, inward on an object's path. Now listen, The force acting inward is called centripetal force. And it always pulls inward. And the reason it goes in a circle is because every second that goes by, it wants to keep going what because of inertia? No, because of inertia, it wants to always go in a straight line. So it wants to go like that, wants to. Its inertia tells it to go like that, but it's being pulled in, and so it ends up going like that. And now here it is, it wants to go like that, but it gets pulled in, and so it ends up going like that. That is circular. That's why when you... I need to... No. I wish I had something that I could spin like a bucket. You know this thing? You know the bucket spinning thing? The reason the water stays in is because inertia holds it there.